on atomic structure. As we talked about in the atomic theory screencast, the modern atomic model is looked at as the electron cloud model. So we found that the electrons are a little more weird than we anticipated, and we'll talk about those. Our next chapter is all about electrons. But we found that we couldn't know certain things about those electrons, like we can't know their speed and location at the same time. We can only know one or the other because the act of observing it changes it. So instead of them being in those little circles like in the Bohr model where he thought that they went around the nucleus, the electrons went around the nucleus like trains on a track or like the solar system, that's a little more fuzzy than that. So we go with the electron cloud, and it deals with areas of probability, and we can only tell the most probable region for an electron, not exactly where it is. So what we have learned from this is that protons and neutrons are located inside that nucleus. And the nucleus is really, really, really tiny compared to the size of an atom. I've heard it where if an atom were blown up to the size of a football stadium, that the nucleus would be a dime in the center of that. So very, very tiny, but that is where those protons and neutrons are located. The electrons are located not in the nucleus. They surround the nucleus in that electron cloud. All right, and so I have a little picture here, just kind of showing you a little representation of the electron cloud model. In the center there is that tiny, tiny little nucleus, and then we have the electron cloud, and you'll see that it fades out as you get further away from that nucleus because the electron density is less in the outer areas surrounding that atom. Okay, now this is kind of a throwback. Probably remember this from your middle school days when we did draw Bohr diagrams. And we're going to look at those because even though Bohr wasn't exactly right with his atomic model, there were pieces of his atomic model that we still hold true today. And his idea of energy levels. So in middle school, you probably drew something that looks like this little structure here, and you have a certain number of electrons that are permitted on each energy level. The energy levels are always numbered from the nucleus out. So if we say that this right here is the nucleus, then our first energy level would be here. Now we usually use N to represent an energy level, so this is N equals 1, and this is N equals 2, and this is N equals 3. And so on and so forth. So as they go further away from the nucleus, they have higher numbers for their energy level. The first energy level can only hold 2 electrons, and then it is completely full. The second energy level can hold up to 8. The third energy level can hold up to 18. Now that's a tricky one, so make sure you memorize that one. And the fourth energy level can hold up to 32. Now it can have more than 4 energy levels, but it just starts to kind of repeat after that. So these are the ones you actually have to remember here. All right, we're going to look at some of these subatomic particles, because atoms are made up of smaller particles. An atom, though, is a substance that still retains the property of the atom, or of the element. So if I have an atom of oxygen, it's going to act like oxygen. But atoms can be broken down into things that are a little bit smaller, those subatomic particles, and again, I expect you to have exposure to those. We'll talk about them. They're protons, neutrons, and electrons. And we'll talk about their symbol because we use lots of symbols in chemistry. It's important to know their charge because we're going to be working with that here a little bit later. And it's also important to know about the mass of each of those individual particles because that does affect the mass of the element or the atom itself. Now, mass is going to be measured in AMU. If you remember from your definitions, an AMU is an atomic mass unit. So they started measuring the mass of these subatomic particles in grams and kilograms. But the numbers are so ridiculously small that they kind of lost meaning. So they needed another unit for atomic mass, and they lacked the creativity to give it a good name, so they just called it atomic mass units. It is based on carbon-12. carbon-12. We are carbon-based life forms, and we're going to find that carbon-12 is a very, very important atom for us, and is the basis for a lot of things, because a lot of things are made up of carbon, us included. So it's just a term of measurement that is related to a gram. All right, so our first subatomic particle is a proton. Proton has a symbol of a lowercase p with a superscript positive sign because the proton is positive. It has a mass of about 1 AMU. This was actually something like 6 times 10 to the negative 27 kilograms, something along those lines. And you don't have to memorize that mass. You need to know that it has a mass of 1 AMU, but I just wanted to show you that they are pretty tiny. Our next one is a neutron. Neutron was the hardest for us to discover because it doesn't have a charge. And the others we could manipulate. You saw in those experiments that we could manipulate positives with negatives and negatives with positives. And we deal a lot with charges in chemistry. But a neutron took us a while to discover because we couldn't manipulate those with charges. So its symbol is a lowercase n with a superscript 0 because it has no charge. It is neutral. That's why it's named a neutron. Now, the mass of a neutron is about the same as a proton, so it's also 1 AMU. Again, it's just slightly heavier, but still about the same kilograms there. All right, now we have our last subatomic particle that we're going to talk about, and that is the electron. The electron is symbolized by a lowercase e with a negative sign. That is because electrons are negative. Make sure that you know that. Now, the mass of an electrons end up being really, really, really tiny, especially compared to the mass of a proton or a neutron. Electron has a mass of like 9 times 10 to the negative 31. So when we go to AMU, this is like 1 over 1840 AMU. And you actually do need to know this one, but in general, we do consider it to not have that much mass. It's just not significant enough for us to calculate when we talk about an entire atom because it pales in comparison to the mass of a proton and a neutron. All right, so when we go into talking about the mass of an atom, the mass of an atom is pretty much composed of the protons and the neutrons. Those are both located in that nucleus. So all the mass of an atom is crammed into that tiny, tiny, tiny nucleus there in the center of the atom. Okay. Now, atomic mass then is equal to protons plus neutrons. We're going to be working with this a little bit later, and you're going to have to be able to find the mass of all kinds of different elements. So you need to make sure that you remember that it is protons plus neutrons. Atomic number is the number of protons. Now, both of these are located on the periodic table, and I'll talk about where that is here in just a moment. Atomic number is the number of protons, and each element has a unique atomic number. The atomic number identifies the atom. So if you find an atom that has 8 protons, it is oxygen, always, always, always. If it all of a sudden has 7 protons, it's no longer oxygen. It is called nitrogen. So the number of protons for an element is not really going to change until we get into nuclear chemistry. So for right now, whatever the atomic number is the number of protons, and that can help you identify what the atom is. Now, I told you this stuff was located on the periodic table. So if you look here, the atomic number is printed on top on our periodic table in the room. It is printed in blue. Then you have the chemical symbol. Remember, it's a capital letter or a capital letter and a lowercase letter. And then the atomic mass is there at the bottom. Here for the next little time, or for the next couple of days, our atomic mass, we're going to round this up to a whole number, but pretty soon we won't be doing that. You can't have 0.01 of a proton or a neutron. This atomic mass is actually an average, and we'll talk about how it's calculated a little bit later. So they take all of the naturally occurring isotopes of the atom, and it's a weighted average of all of those together. But you would not find a particular atom that has a mass of 12.01. It might be 12, it might be 13, it might be 14. They're going to occur in whole numbers. And that number is in red on your periodic table. If you're not able to see the periodic table, that's why you have your own copy. So go ahead and you can have that out as we're working with these. All right. Now, we're going to start dealing with our structures and being able to calculate the different subatomic particles in each atom. Now, one that we haven't talked about is an electron. If an atom is electrically neutral, that means the positives balance the negatives. The protons equal the electrons. But that only occurs in an electrically neutral atom. They're not going to stay neutral for very long, but we'll practice with them here in a second. If it's neutral, protons equal the electrons. But we're going to find that electrons can be lost or gained during chemical reactions. Alright, so what I have here is a little table, and we're going to see if we can figure out these different, the ones that are not filled in. And we'll try and figure them out with the formulas that I just went through. So, first we're dealing with oxygen, and then ask for its symbol. That we can look up on the periodic table. Its symbol is O. And you have a periodic table with all the names on them, so you should not make a mistake here. They give us the number of protons here for oxygen, that it is 8. Well, the number of protons is equal to the atomic number. So the atomic number here is 8. The number of protons for a neutral atom of oxygen is also equal to the number of electrons. So our positives balance our negatives. And so if it has 8 protons, it's going to have 8 electrons. Now, we need to figure out the number of neutrons for oxygen. So what we're going to do is we know that mass is equal to protons plus neutrons. That's supposed to be a plus sign. All right. So if I have the mass and I have the number of protons, I can figure out the number of neutrons. So if I just rearrange that equation and subtract the protons from each side, I get the number of neutrons is equal to the mass minus the number of protons, or the atomic number, either one, because protons is equal to the number, or to the atomic number. So my mass in this case is 18. I subtract out 8. And so I have 10 neutrons. And I can recheck that. Oops. I can recheck that. My protons plus my neutrons should equal my mass number. So 8 plus 10 does equal 18. Okay, now we have a different set of things given to us for potassium. So potassium is K on the periodic table. You're going to find it all the way to the left. And they give us the atomic number. Well, we know the atomic number is equal to the number of protons. So if it has an atomic number of 19, it has 19 protons. Also, we know that if it is electrically neutral, and these are for right now, then the number of protons is equal to the number of electrons. So if I have 19 positive things, I've got to have 19 negative things to make it electrically neutral. Now I have to figure out the mass number. So mass is equal to protons plus neutrons. So 40 plus 19 is going to give me a mass of 59. Alright, and that's how you figure out the different types of, or the different things that are given in atomic structure. So you will have some of this to do in your assignment after this video cast, and just use the formulas that are given. So mass is equal to protons plus neutrons, atomic number is equal to the number of protons, mass right now, and I will okay, sorry. Right now what you need to do is figure out how many protons, neutrons, and electrons are in an atom of fluorine with an atomic mass of 19. At this point, you can pause the video cast, take a moment, see what you can get. Okay, so what we have right now is an atomic mass of 19. We're dealing with fluorine. Fluorine on the periodic table is number 9. So that is its atomic number, that number in blue, so that means it has 9 protons. If it is electrically neutral, it also has 9 electrons. The mass will help us figure out the number of neutrons, so that's going to be our mass, which is 19, minus the number of protons, which is 9. And so I end up with 10 neutrons for that one, for a neutral atom of fluorine. Okay, now, what if it's not electrically neutral? Then it's called an ion. Now, we're dealing with a lot of vocabulary here. You had vocabulary to do for homework last night. Make sure that these words make it into your head. You have to know the difference between an ion and a neutral atom, and an isotope, which we're going to get to here in a second. Ions are atoms or group of atoms that have a positive or negative charge because it has lost or gained electrons. So for the time being, until we get to nuclear, the number of protons for an atom is not going to change, but the electrons do. Sometimes they gain them, sometimes they lose them. Now you have to remember that electrons are negative, and you have to think about it that way. So we're either going to be adding a negative, or we're going to be removing a negative. And so it's a little different to think about. If you add an electron, things become more negative. If you remove an electron, they become more positive. All right, so for our ions, if you're trying to find the charge, it is equal to the number of protons minus the number of electrons. And whatever number that will give you the charge of the ion. So here is magnesium 2+. So you're going to see the charge located in this upper right-hand corner next to an atom. So magnesium with a 2+ charge and it has a mass of 25. To find the number of protons, neutrons, and electrons. Well, magnesium on the periodic table is number 12, and so it has 12 protons. It also is going to have, figure out our neutrons. Our neutrons, it's going to be our mass, which is 25, minus the number of protons, which is 12, which leaves me with 13 neutrons. Now I have to deal with the number of electrons, and here's kind of how I deal with that one. I look at the charge. Is it overall positive or negative? Well, it's positive. So that means I'm going to have 2 more positive things than negative things. Or it also means that I have lost 2 electrons. Because remember, electrons are negative, and if we lose 2 negative things, we become overall positive. So I have lost 2 electrons. If it were electrically neutral, I would have 12 because it would match the number of protons. But I've lost 2, so that means I have 10 electrons. And that takes a little getting used to. Okay. Now, we're going to talk about some notations. This is pretty important, and you will be practicing this. So, we have 2 different notations. The first one we're going to talk about is nuclear notation. Nuclear notation is going to let me see if I can move my board here. Look like this. So you have your element symbol. That's the big one. In the upper left, you have the mass, which is your protons plus your neutrons. Your atomic number, or number of protons, is at the bottom left. And at the top right is your charge. So let's look at some examples of that. nuclear notation for a neutral atom of nitrogen would look like. If it doesn't have that charge in that upper right-hand corner, that means it is electrically neutral. So, we want to figure out how many protons, neutrons, and electrons this has. So, the bottom number is going to tell us the number of protons. So, I have 7 protons. Now I have the element symbol, so we know it is nitrogen. I have the number of neutrons to figure that out. The number of neutrons is going to be 14, which is our mass number, minus the number of protons. So that gives us 7 as the number of neutrons for this one. And for our electrons, since we know it is electrically neutral because of the absence of the charge, then our protons equal our electrons, and that is 7. Okay. Now, if it were an ion, it would look something like this. In this one, again, our number of protons is located at the bottom, and that's 7. To find our mass, all you have to do is subtract these two numbers from each other. So, my neutrons is 14 minus 7, which would be 7 neutrons. In this case, I have a charge. So that means I've gained or lost electrons. It's negative. That means I have gained electrons since they are negatively charged. How many have I gained? 3. If it were neutral, I would have 7, but I've gained 3 more, so that gives me 10. So you always start with where they were neutral, and then you make the changes based on the charge from there. Okay. I'm going to give you a chance to practice. I want you to find the number of protons, neutrons, and electrons in these 3 ions. Pause this video cast or screencast right now, and then work on these, try and find the numbers of protons, neutrons, and electrons. Okay, so now we have to calculate the answers here. So for nickel, we need our number of protons. That's located at that bottom number, so we have 28 protons. The number of neutrons is going to be found by subtracting these two numbers. So 59 minus 28 is going to give us 31. And that's how we get our number of neutrons. Now, if it were an electrically neutral atom, we would have 28 electrons. And but our charge tells us that we have gained or lost electrons. This is a positive charge. That means we have lost 2 negatively charged electrons. So remember, those electrons are negative. And so we've lost 2, which means that instead of 28, I'm going to have 26 electrons. All right, now with aluminum, we need our number of protons. That's that bottom number right here, so 13 protons. To get our number of neutrons, we're going to subtract these two numbers. So 27 minus 13 is 14. Then we have to deal with the number of electrons. If it were electrically neutral, we would have 13 electrons, so that would be equal to the number of protons. But we know we have a difference of electrons because of this charge right here. It is positive, so that means we have lost electrons, and we've lost 3 electrons. So that means instead of 13, we're going to have 10 electrons. All right, now we have selenium here, which was in Dandruff shampoo. We've got need our number of protons, and that is 34, because that bottom number tells us that. Then we're going to deal with our number of neutrons. We're going to subtract those two numbers, and you're going to end up with 45. So 79 minus 34 is 45. And if it were electrically neutral, we would have 34 electrons. But we have gained or lost electrons because of we have a charge here. We have a negative charge, so that means we have gained electrons. And we have gained 2 of those. So instead of 34, we're going to have 36 electrons in this particular ion. All right, I have one more for you to try, and that is here. I've just kind of turned it around. I'm giving you the number of protons, neutrons, and electrons, and I want you to use the periodic table and try to figure out what element it is and write the complete symbol in nuclear notation. So they should end up looking like what we started with up here. So pause this screencast right now, work on that, and then we can restart and I'll give you the answer. Okay, so the complete symbol for this, we have to figure out what element it is, and one subatomic particle identifies the element, and that is the number of protons. The number of protons is the atomic number, which we can find on the periodic table. On the one in the room, it's going to be that top number in blue. So we look for number 21, and it is SC, scandium, named after where it was discovered. Now, at the bottom, that's the easiest, we're going to start, and what goes here is the number of protons. I have 21 protons. What goes up here is the mass. The mass is equal to the protons plus the neutrons. So not just the neutrons, both of them added together. So you should end up with a 45 up here, the 21 plus the 24. Now we have to deal with the charge. So the charge has to deal with the positive things and the negative things. The easiest way to go with this one, to know which way it's going to be, positive or negative, is to see which number is the biggest, and the number of protons is the largest. And so that means it's going to be a positive number. Now, how much more positive is that one, or how much bigger is 21 from 18? Well, it's 3, so that means it's 3 positive. I have lost 3 electrons, giving this ion a charge of 3 positive. Now, that is nuclear notation. There is one other notation, and it's called hyphen notation. And in hyphen notation, there's a hyphen. And the way it looks is it's the element, write out the element's name, you put a hyphen, and then you write its mass. So the example I have here is for calcium, calcium hyphen 40. You have to remember that this number right here is the mass, which is your protons plus your neutrons. So if we are trying to figure out the protons, neutrons, and electrons from hyphen notation, one thing is they have to be electrically neutral. So your protons will equal your electrons if it is in hyphen notation, because there's no place to put a charge like there is in nuclear notation. So for this one, the number of protons, the way I have to find that is I have to look up calcium on the periodic table. I find calcium on the periodic table. It is number 20, so that's its atomic number, which is equal to the number of protons, so that's 20. Since this is in hyphen notation, it has to be electrically neutral, so the positive have to balance the negatives. So if I have 20 protons, I got to have 20 electrons. Now, to find the number of neutrons, I'm going to take the mass, which is given to me right here, and it's 40, and then I subtract out the number of protons, which I got from the periodic table, and that gives me 20 total neutrons. And those are the 2 different notations for atomic structure, and a little bit about each of those subatomic particles.